Good morning. Okay, we continue with STOF systems subjected to general loading with one example. Okay, in the vibration testing of a structure, an impact hammer with a load cell to measure that the impact force is used to cause excitation, as shown in figure. Assuming M is equal to 5 kilogram, the mass of this structure is 5 kilogram. The stiffness is 2000 Newton per meter. We can estimate the base of this structure as a linear spring with the stiffness 2000 Newton per meter. C, or the damping constant, is 10 Newton second per meter. And F, the force, the amplitude of the force or the amplitude of the impact is 20 Newton second. Find the response of the system. Here we deal with an impact or an impulse in terms of mathematics. So we can write the response of the system by using the function gt that yesterday I explained how to extract this as the response for the system subjected to impulse. Only we need to obtain the natural frequency and the damping ratio for this system. So we can calculate the natural frequency. We have the stiffness, the mass, and also we can calculate the damping ratio because we have the damping constant, and the amplitude of the impulse is 20, the magnitude is 20 Newton second. So we can substitute into the equation and obtain the response easily. So as I told you, you can obtain the natural frequency, which is equal to a square root of k divided by m. So easily we can obtain that the natural frequency of the system is 20 radian per second. The damping ratio, which is the ratio of C to the critical damping constant, or 2 times by m times by omega n. Then we can substitute and obtain that the damping ratio is 0.05. So we deal with an underdamped system. We can calculate the frequency of the damped vibration, which is omega d, and it's a function of omega n and psi, or the damping ratio and the natural frequency, and it's equal to 19.98. As you can see, because the damping ratio is very small, the frequency of the damped system is almost equal to the frequency, the natural frequency of the system. So we have omega d, psi, and omega n. So easily you can substitute into the equation for the response, this equation, this formula. We have omega n, psi, omega d, m, and also we have the magnitude. So we can substitute here and obtain the response for this system. So of course, as I explained yesterday, the purpose of using this equation is not to solve the equation for the system subjected to the impulse. This is, in fact, this formula is used to obtain the response of the system under a general forcing. And today we will discuss how we can expand this solution for a system with a general forcing, which is not periodic or harmonic, and we can use this equation to obtain the response in subjected to the general condition. Okay, the next example, we want to find the impulse response functions of a viscosely damped spring mass system for the following cases. Case A, an undamped system. So damping ratio and the damping constant is 0. Part B, for an underdamped system. So the damping ratio is between 0 and 1. Part C, critically damped when Psi is equal to 1. And finally, for an overdamped system, when Psi is more than 1 or the damping ratio is more than 1. For part A, when we deal with an undamped system, we know that Psi is 0 and omega d, or the frequency of the damped vibration, is equal to the natural frequency of the system. So if you substitute this value into the equation for the impulse uh, response, you can extract that xt is equal to 1 over m omega n, which m is the mass of the system, omega n is the natural frequency, and this is sine omega n t. So this is the response for an undamped system. Part B, for an underdamped system, we obtained yesterday, and in the previous example we used this equation. This is for an underdamped system. Part C, we want to obtain for a critically damped system. For a critically damped system, we know that xt is equal to this term, c1 plus c2 times by t times by exponential minus omega nt, which c1 and c2 can be obtained from the initial condition as a function of x naught and v naught, which x naught is initial displacement and v naught is the initial velocity. Omega n is the natural frequency of the system. And if you substitute this, you can obtain the constant coefficient by using the initial condition. Once again, if we want just to remember you and just to remind you, and if you remember, xt for a system with critically damped, xt was equal to c1 plus c2 times by t times by exponential alpha t, which alpha was the root of the characteristic equation. And you know that the characteristic equation for a system with critically damped, it has a general form. Of course, we can call it alpha 1, for example. The general form of the characteristic equation is alpha minus alpha 1 squared is equal to 0. And we have a double roots at alpha 1. So the homogeneous response, or the transient solution for the system with critically damped when Psi is equal to 1, is in this form, c1 plus c2t exponential alpha 1t. And then we can use the initial condition. At t is equal to 0, x must be equal to x naught, and at t is equal to 0, x dot, or the velocity, must be equal to v naught. So from here, from this initial condition, we can extract c1 and c2 as a function of x naught and v naught, which c1 is in fact x naught, and c2 is equal to v naught plus omega and x naught. This is c1 and c2. And now we need to substitute the numerical value for x naught and v naught according to the impulse excitation, and then we can find the total response for a critically damped system subjected to an impulse. So you can see this is the procedure. Of course, we explained and we studied this procedure when we studied and investigated the system with critically damped and when Psi was equal to 1. Okay, so you can refer to the lecture notes again and you can see. The next step, we need to use the initial condition. You know, when the system is subjected to an impulse with magnitude 1 or unit, the initial displacement is 0 and the initial velocity is 1 divided by m. Yesterday we extracted these results. Now if you substitute x naught is equal to 0 and v naught is equal to 1 divided by m, this term is 0, this term is 0, and only we will have 1 divided by m multiplied by t multiplied by this exponential term, and it is t over m exponential minus omega n t. So you can see this is the response of a critically damped system subjected to an impulse with magnitude unity. Okay, and finally part D, the response of an overdamped system subjected to an impulse. Again, we have the response in this form. You know, when we deal with an overdamped system, the roots of the characteristic equation are equal to alpha 1 and alpha 2, which alpha 1 is equal to this term minus psi plus the square root of psi squared minus 1, and alpha 2 is minus psi minus the square root of psi squared minus 1. And because psi is more than 1 in a system with over damped damping, so this phrase under the radical is positive, so this is a real, and this is a real integer, real number. Of course it's not integer, it can be in fact a real number, and we will have two distinct real number as the roots of the characteristic equation, and the total response, or the homogeneous response, of course, is equal to C1 exponential alpha 1t plus C2 exponential alpha 2t. Now we need to obtain C1 and C2 by using the initial condition. Again, we use this initial condition for a system subjected to the impulse. So we substitute this initial condition at t is equal to 0. The displacement is 0, and at t is equal to 0, the velocity is 1 over m, which m is the mass of the system. Now we can use this information and find C1 and C2 and obtain C1 and C2 as a function of mass omega n and damping ratio. So this is the response for an overdamped system, and we can use this. Of course, here this is a typo error. This term shouldn't be here. This is for the previous part. Here for part C, I should remove this term from here. From this initial condition, you can obtain C1 and C2, two constant coefficients. And then when you substitute C1 is equal to this term and C2 is equal to this term, this is the XT, the response of the system with overdamped and overdamped system. Okay, any question? Is it clear so far?
Yes.
Okay. Now we want to use the response of the impulse to find the response of a system subjected to a general force. Here we can assume that we have an external force Ft, which has a general form like this. You can see it can be an arbitrary function of time, of course a continuous arbitrary function of time, and we can assume that this Ft is a series of impulses with varying magnitude. For example, at t is equal to tau, at this point, we can assume that the impulse has a magnitude of f tau. So you can see, you can model any type of general forces or any type of general functions in terms of mathematics. You can model any function ft as a summation of a series of impulse with varying magnitude, as you can see here. Now, the response of the system subjected to this force, this general form force, by using the superposition principle, we can find the response. Of course, the particular response is a summation of the response of the system to each of these impulses. So we can write that the xt, the response, the total response, of course, of the system to this general force ft is equal to the summation of f tau, which is the magnitude at t is equal to tau, times by gt minus tau, which is the response at the response of the system at t is equal to tau to the impulse gt, and multiply by delta t. So you know from mathematics, when delta t goes to 0, we can convert this summation into the integral, and we can write that xt is equal to the integral of 0 to t f tau gt minus tau d tau, which f tau is the general form, or the general form of the external force or function ft. Instead of t, we can substitute tau. Gt minus tau is the response of the system to the impulse at t is equal to tau, and 0 to t is the duration of the time, or the period of the time that the force F is inserted to your system. So by using this integral, you can find the response xt, which is the response of your system to any arbitrary continuous function of time, and we can obtain to the response to any form of ft. Here you can see that ft is not periodic or it's not harmonic, but we can obtain the response to any type. Only we need the general form of this ft. I mean, you should find a function which is fitted to this curve. For example, you can fit uh, by using the curve fitting method, you can find that ft, for example, is an, for example, a polynomial from, for example, order 5. So it will be, for example, c1 t5 plus c2, for example, t4, and so on. So you only need to find the form of this function ft, and then substitute into this integral and calculate this integral. And also we have gt minus tau, which is obtained yesterday, and in the previous example I used this gt. So you only need to substitute here and calculate this integral using any uh, method. Sometimes you can analytically solve this integral and obtain the response, but sometimes it's not possible to solve this integral analytically, and you need to use numerical methods to obtain the response of this integral, because sometimes it will be a complicated form, sometimes ft, because it has a general form and it has an arbitrary form. Maybe you cannot find an analytical solution for this integral, so you can use the numerical methods to solve this integral. Now if you substitute the gt for your response, here instead of gt you substitute the response, you know that the gt is equal to exponential minus psi omega and t sine omega dt divided by m omega d, which instead of t you should substitute t minus tau, because this is the gt minus tau. So this is the gt minus tau. Of course we have divided by m omega d, and now you need to only solve this integral when you substitute f tau you can solve this integral and obtain the xt, the response of the system. There are some points regarding to this formula. First of all, this equation, this formula, and this method does not consider the effect of the initial condition. As you see, we only solve the response for each moment by assuming that the structure is subjected to an impulse at that moment, and then we solve and obtain the response. So the initial conditions is not considered in this solution. And sometimes when you want to study the behavior of your structure at the initial moments, maybe this response cannot give you an exact or an accurate solution, and because it does not consider the initial conditions. But when you deal with a steady state response, and when you deal with the behavior of your structure for a long period of time, this is definitely a suitable method and you can use it. Another point is that we call this equation the convolution or the Hamel integral. Any times when you heard something about the convolution integral, in fact, this is the convolution integral, and you are using, in fact, the convolution integral. That definitely you heard about this in the mathematics courses, and this is the application of the convolution or the Hamel integral. And finally, usually the ft here, as I told you, has a form that permits an explicit integration. You can solve and analytically find the response for this integral. But in such cases that the integration is not possible and you cannot find an analytical method, you can find the response and you can obtain the response xt by using the numerical methods. And again, the numerical, there are a lot of numerical methods that for example, the Gauss integral method you can use, or the weight Gauss integral methods, you can use different numerical methods to obtain the response of this integral by using the numerical methods, because sometimes this ft has a complicated form and you cannot easily solve this integral and obtain the xt. So this is the total procedure. As you can see, we use the impulse function response to obtain the response of the system to a general non-periodic force. This is the first method, and later next week we discuss the Laplace and numerical methods as well. So any questions so far? Is it clear? Okay, we can consider an STF system which is under an arbitrary base excitation, similar to the, as I told you, when sometimes we have external force, we have the non-homogeneous term as an external force, and sometimes we have the non-homogeneous term uh, as a base excitation. In all of these cases, you can consider these terms as a non-homogeneous term. When we have base excitation, by defining a new parameter z, which is equal to x minus y, we can extract the equation of motion as a function of z. As I told you, z is equal to x minus y, and it's equal to mz double dot plus cz dot plus kz is equal to minus my dot. You know that z is x minus y, so here it will be x double dot minus y double dot, and also here instead of z dot we will have x dot minus y dot, and z which is equal to x minus y. If you substitute z is equal to x minus y into this equation, you can extract the same equation, which is mx double dot plus cx dot plus kx is equal to cy dot ky plus ky. But here, when you use this new parameter z and new variable z, in fact, you can write the equation of motion as a function of z, and we have the external force, which is a function of y, or y double dot. Now this is your non-homogeneous term, or this is your ft. So in your equation for the convolution integral, you can substitute for ft and m times by y double dot. Of course, we have one negative as well, and you can simplify and obtain the zt, or the response of your system. As you can see, this is the response of your system, zt. And then when you want to obtain xt, you know that xt is equal to z plus y. So once you obtain the zt, and definitely we have the yt, because y is the function of the base excitation. So xt is equal to zt plus yt. So you can obtain the xt from this equation, or you can directly solve your the equation for x. So it's up to you. And you can see we can use the convolution integral for the system subjected to the base excitation, when this base excitation is not a periodic or harmonic function. It's a general non-periodic function of time. And then you can again use the convolution integral, similar to the case when we have the external force. Okay, so the procedure and the response solution is the same. Okay, we have one example to understand better the application of the convolution integral. We have a vehicle traveling at a constant speed v in the horizontal direction, encounters a triangular road bump as shown in figure. Treating the vehicle as an undamped spring mass system, it means we don't have damping. C is equal to 0. Determine the response of the vehicle in the vertical direction. So we have a bump with this dimension. Y is the heads, the length of the bump is delta, the velocity is v, which is a constant velocity. So we can use the velocity v and this length delta and find the frequency of the motion during encountering this bump, and then we can find the response of the system to this base excitation. As you can see, this base excitation is not a periodic base excitation. I mean, we only have one bump, and after that the road will be again there is no bump after this. So it's not periodic, it's not harmonic, and it has a general form. So we can model this bump as several impulses. Here you can see, so we can assume at each moment there is an impulse. Only the magnitude of the impulses are increasing by time. So we can find the response using the convolution integral for this term. For this purpose, we need to obtain the natural frequency and substitute into the equation. So yt, yt in fact is y times by vt divided by delta, when t is between 0 and delta divided by v. You know, at t is equal to delta divided by v, this car will be located here. This is t is equal to delta divided by v, and this point is considered t is equal to 0. So our point time origin is this point, t is equal to 0, and t is equal to delta divided by v, because we know that the velocity of this vehicle is v, and we know that x is equal to v times by t. When x is equal to delta, this is the delta, so time is equal to delta divided by v. So at this moment, we will be here, the car will be located at the end of the bump, and after that you can see that y is equal to 0. Okay, So if you assume that this is the axis of y and this is the axis of t, of course this axis, the vertical axis, must be located here. I write here because it's here, it's not clear. So y t as a function of time started from here and it will increase by time till you achieve this point. T is equal to delta v, and after that again you can see that yt is 0. So for t more than delta divided by v, yt is 0, but for t between 0 and delta divided by v, yt is equal to yvt divided by delta, which yvt divided by delta is the equation for this line. You know, we have the slope of this line. The slope is y, this y, of course, the uppercase y, divided by delta times by v and times by t will give you the position of this point or the equation of this line as a function of time. Now we can substitute this equation for yt in the equation of motion, but we need to extract the equation of motion. If you use the Newton's second law and write the Newton's second law in the vertical direction and plot the free body diagram for this mass m, we will have the force due to this spring here, which is equal to k times by x minus y, which x is, for example, x is in this direction, this is the x, or it can be in upward direction, and this is the y, the position of the lower edge of the spring. So the force in this spring is equal to the k times by x minus y or k y minus x. It depends on the direction of your force. And also we have the weight of this mass m, we have mg, but because this weight will cause some initial deflection in the spring, so we neglect this weight and we ignore it in the equation of motion, and we will have only the force due to the spring, and it must be finally equal to the mass times by the acceleration, which is mx double dot, and you can finally extract the equation of motion in this form. So equation of motion is mx double dot plus kx. As you can see, we don't have any damping terms, we don't have x dot because there is no damping, and it must be equal to k times by y, which this is the non-homogeneous term in your equation of motion, and y, this y will be substituted from here, which is a function of time. So mx double dot plus kx is equal to kyvt divided by delta, and it's equal to 0 for t more than delta divided by v. So we need to obtain the response for the system first for this period of time, and after this for t more than delta divided by v. So we have one response for this period of time and one response for here. As you can see, for part 1 you can obtain the total response using the convolution integral, but for part 2 we deal with a homogeneous equation. In part 2 we have mx double dot plus kx is equal to 0. Yes, so this is a homogeneous response, but to solve this equation you need some initial condition, definitely, and these initial conditions are the displacement and the velocity at this point. T is equal to delta divided by v. So x at t is equal to 0, or the initial condition for the second equations, in fact, are the response and the velocity obtained from equation 1, this equation with this non-homogeneous term, at t is equal to delta divided by v. So once you want to solve the second equation, you can consider another origin for your time at here at, for example, t prime, and you can assume when t prime is equal to 0, t is equal to delta divided by v, and you can use the response of the first equation to obtain the initial condition for the second equation, which is an homogeneous equation, and you can solve it. But here we only want to discuss the response for part one using the convolution integral method. As you can see, when t is between 0 and delta divided by v, the particular response is equal to this formula, which is the convolution integral kvy, which all of them are constant value. K is the stiffness, v is the velocity of the system, and y is the height of this bump. M is the mass of the system, delta is the length of the bump, and omega n is the natural frequency of the system, and it's equal to a square root of k divided by m. And then you need to calculate this integral, tau times by sine omega n t minus tau and d tau. So you need to calculate this integral. And finally, the particular response for t more than delta divided by v is 0, because there is no homogeneous term here, you can see. So the particular response is 0. We can solve and obtain x pt by solving this integral and obtaining the response for this integral. You can solve and obtain, which is equal to vy divided by delta omega n times by omega nt minus sine omega nt. This is the response for t between 0 and delta v, delta divided by v, sorry. And the response, the particular response after this time is 0. But after this time, we can obtain the homogeneous response, because definitely we have the homogeneous response. The homogeneous response for this period of time is considered in here, okay? And in fact, because the initial condition, by assuming that the initial condition is 0, we can neglect the homogeneous response for this period of time. But after that, for this period of time, when t is more than delta divided by v, we can use this response to obtain the initial condition. I mean, we know that xt is equal to this term. So at t is equal to delta divided by v, we need to substitute here instead of t. You should substitute t is equal to delta divided by v. We can obtain x naught. And for v naught, we can find the derivative of this term, the derivative of xt or x dot, which is v. And then again, substitute t is equal to delta divided by v. And then we can extract v naught. So this x naught and v naught are initial condition for this period of time when t is more than delta divided by v. And now we can solve the homogeneous equation, this homogeneous equation, and use this x naught and v naught to obtain the homogeneous response for this time after t is more than delta divided by v. Okay, any question? Is it clear? Okay. Okay, as I told you, you can use the initial condition. Only here we discuss the particular response. For the homogeneous response or transient solution, you can use the initial condition, and as I explained, you can use to solve and obtain the homogeneous solution. Okay, the next example here, we have a compacting machine modeled as a STF system is shown in figure. The force acting on the mass M, which M includes the masses of the piston, the platform, and the material being compacted, due to a sudden application of the pressure, can be idealized as a step force. Here you can see determine the response of the system. Again, here you can see that Ft, or the external force, is not periodic. This is a step force. It starts at t is equal to 0. It has an amplitude f naught, and it will continue and will remain the same. So it's not a constant, sorry, it's not a periodic, and this is a constant function. So we need to obtain the response of this system with mass m, stiffness k, and damping constant c to the external force Ft, which is not periodic, and it's only a constant external force. So again, we need to use the convolution integral method. This time Ft is a constant value and it's equal to f naught. You need to obtain omega n, omega d, and substitute into your equation, and also the damping ratio psi. Once you substitute, you can solve this integral and obtain xt. You know that when you solve this equation, this is the integral of exponential times by sine function. So you can use different methods to solve these type of integrals and obtain the response xt. And once you substitute the numerical value for omega and omega d and damping ratio, you can extract the numerical form for xt, and f naught, which is a constant value, it's the amplitude, this term, for your external force, and m is the mass of the system. Okay, so easily you only need to substitute here. Maybe your main challenge is to calculate this integral, and you can easily solve this integral by using different methods. Of course, I have uploaded some files on Moodle. You can use this formula and these methods to solve this. And if you don't have any question from this example, I can show you how, and the formula which is uploaded on Moodle, and you can use it to solve this type of integral, because I believe in that your main challenge in this chapter is to calculate this type of integrals. Any question from this procedure? Okay, so let me show you. Okay, if you go to your Moodle page, I think here in week 7, the tabular method for integration by parts. So under the section week 7, you can see this file, which is the tabular method for integration by parts, and you can use this method. Here you can see I prepared 2 examples, and you can see different. Here, for example, we have the integral of a polynomial multiplied by a cosine function, how to use the tabular method, and you can use the integration by part method to find the response of this problem. Or here we have the integral of an exponential term and sine function, and again we are using the integration by parts and find the response. Of course, definitely you had these formula and these methods in your previous courses, and you can, here only I just want to remind you how to use this method. If you had any question or if you had any problem, you can let me know and I will explain more. If you need any further explanation, we can arrange a meeting, and again I can explain more if you need it. But I guess that you know how to use this formula because these are related to your previous mathematical course. Okay, if you don't have any question, you can wrap up this session. After 10 minutes break, we can start the tutorial session. Any question? Okay. So we will have 10 minutes break, and after that I will start the tutorial and explain the tutorial problems. Thank you.